Building an autonomous aircraft is within reach of talented students, but it's definitely not the easiest thing in the world either. There are many ways to fly, and even more ways to put together the electronics and software that an aircraft needs to fly by itself. This year we have all kinds of airframes, many of them custom designs, from traditional fixed-wing airplanes to a whole bunch of exciting rotary wing entries, including traditional helicopters, hexacopters, and a possible world-first autonomous autogyro. In terms of payload, well, there's just too much variation to list. Let's go visit some of the teams and have them walk through us what makes their robots special.
We use a Piccolo autopilot to control the plane. So what that does is that controls all the servos on each of the control surfaces that we have, the ailerons, the flaps, and rudders. We also have several sensors that go along with that, a magnetometer and a laser altimeter to help the plane know where it is when it's flying. On the imagery side, we have an MPERX camera that takes very high quality images and a onboard computer that we use for image processing. And we have a high-speed data link down to the ground so that our operator can be looking at these images as they're being taken and submit them to the judges.
So we chose this airframe mainly for the size and also for its really solid aerodynamic abilities so that we would have a nice basis no matter what kind of changes we made to it. So we didn't really foresee design changes, but we kind of kept that option open. For our payload system, our payload is the phone and it's attached here. We have a dampening system consisting of earplugs and rubber bands, and it'll be velcro to this gimbal that we have right here that's attached to a custom-made acrylic, and it fits into our prefabricated model. And so that's our payload mount, and it's hopefully going to give us a really nice noise mitigation for our aircraft.
Well, this is the first autonomous autogyro in the whole world. The main advantage of the system is the simplicity of the system and the possibility of doing things that the helicopter can't. So this is the engines, twin, because we think that maybe it's the first twin gyrocopter engine in the whole world. This rotor is completely made by us, it's custom made.
Just about everything we have on here is custom made. We put everything together ourselves. All the carbon fiber framework is custom designed, custom built. And this frame is a newer design where we have these spars modular, because as we crash them, we keep breaking the spars, and so this one allows us, if it breaks the spar, we can just put on a new spar rather than start completely over on the frame.
This one is what we call a hybrid manufacturing process, where we are merging 3D printed and direct digital manufacturing with some traditional manufacturing methods. So people can see the process here, but here these are the 3D printed structures combined with some other ones. It just allows for complicated structures and extremely rapid manufacturing time. And this is one of our first successful models here for an entirely 3D printed airframe. All the internal structures and everything, the motors bolt straight in. This right here is going to be the future of the University of Missouri, is 3D printing these planes.
That's what makes a competition like this great. It's real-world engineering meets the technological cutting edge, and it's all led by the students themselves. You can't get an education like this in the classroom alone. I can't wait to see how they perform up in the air on the mission course. You can follow along with me at robonation.org, as well as find the information you need to get your school involved.